All right, what we're going to be looking at now is the reductive amination reaction. All right, so this is the best way to get a primary amine to react with a aldehyde or a ketone. All right, we're going to draw aldehyde here. And this is going to give us something called an aminium ion. And then what we're going to be able to do is take that aminium ion and reduce it. So when I got that H in brackets, I'm talking about reduction again. All right, and this is going to give us a secondary amine. So if you notice, we're going from primary amine to secondary amine. All right, very clean reaction. Likewise, if we take a secondary amine and react it with an aldehyde or a ketone, now most times this is done with aldehydes. They're much more reactive in these reactions, although it will work with ketones. All right, so if we take a secondary amine, react it with an an aldehyde, we're going to get an aminium ion as well. That if we reduce it, we'll get a tertiary amine. Okay, so secondary going to tertiary. Admittedly, if you took ammonia and reacted with an aldehyde and went through the same process, you would wind up with a primary amine. But again, we've seen several ways in which to make primary amines. The reductive amination is really a go-to method for making secondary and tertiary amines. All right. So how does this work? All right. So what we're going to do is we're going to look at the mechanism for this. And what I'm going to do is I'm going to take an amine, and let's just keep it simple and look at methylamine. And I'm going to react it with benzaldehyde. All right, so pH for my phenyl group, and we have an aldehyde here. And it turns out that benzaldehyde is not electrophilic enough to allow attack by this amine. So what we're going to have to do is activate it, as we've seen before. So the way we're going to activate it is by using mild acid. Now, if we have too much acid, this reaction gets slowed down. So you kind of want this Goldilocks pH range between about 5 and 7, all right, for this to go. So you just need a little bit of acid. So what you'll typically see is something like mild written in the reaction scheme, or pH above 5, for example. All right, so we're off. And what we're going to do first is activate our aldehyde by treating it with that mild acid there. And again, this is to get this reaction to go. Just a catalytic amount there. All right. So what we now have is an activated aldehyde, and we can now use methylamine as a nucleophile. So we're going to have nucleophilic addition to our activated aldehyde, and that's going to give us our tetrahedral intermediate. All right, since we're an acid, a tetrahedral intermediate will only collapse to kick off a protonated group. So right now, this is set up for oxygen to collapse down and kick off nitrogen, which would send us in reverse. So if we want it to go the other way, well, oxygen's going to have to come in here and get the proton from nitrogen. Then oxygen will be the leaving group, is what we want to go forward. Okay, and as we'd expect, nitrogen is going to form the double bond now and throw out oxygen. All right, so I'm going to go on to the next slide and draw our key intermediate in this process. All right, so our key intermediate is this guy here called the aminium ion. All right, and we've got water floating around as well. All right, actually 2 moles of water, but nonetheless, we have water floating around. And the reaction can, go back and forth, and we're not really getting anywhere. All right, every step's been reversible thus far. But if I get clever and throw in a reducing agent that is mild enough to reduce only the iminium ion, I can get this reaction to go exclusively to the right and never come back. So we can have an irreversible step. And that reducing agent was designed specifically for this reaction. And it's called sodium cyanoborohydride. All right, so it looks a little funky. So why does this one work? All right, so remember, hydride is a delta minus hydrogen, and that's because now it is bonded to a boron, which is more electropositive, so we've got a delta minus on our hydrogen. However, we know that the cyano group is a strong electron withdrawing group, or an EWG. So what it's doing is it's pulling electron density away from that hydride over there. All right, so our hydride, having its delta minus diminished, is going to be a much more mild, I'll put a little tiny delta minus there, reducing agent. All right, when we put this all together, I'll explain why we want it to be mild. We want it just reactive enough to reduce the iminium ion, but not reduce anything else in solution. So again, I'll come back to that. But what we're going to do now is we're going to have a final reversible step here, or sorry, final irreversible step. Okay, and there we go. So irreversible here. And as you can see, we have a secondary amine. Okay? Secondary amine, beautiful. So what we've done is we've converted a primary amine right here to a secondary amine. So the question is, why do we need this weird looking reducing agent, this sodium cyanoborohydride? So let's put it all together again. Aldehyde. And let me change the color of this R group. Let me just change the color of the amino group altogether. And what we need here is H3O plus and sodium cyanoborohydride. All right, so that's how we typically write out sodium cyanoborohydride. We have the BH3 followed by CN. All right, what we're going to get is the RH that is left on the aldehyde is going to now be bonded to the nitrogen. Okay, the oxygen leaves, it's kicked off by that nitrogen, remember? And we're going from a primary amine to a secondary amine, so one of the hydrogens makes it along with the nitrogen, and the other one does not. All right, so what have we essentially lost? We've lost an oxygen and 2 hydrogens to make H2O. So where did that hydrogen come from to make H2O? Because we lost 1 from the nitrogen, and we lost 2 from the acid, if you will. All right, so there's our secondary amine. So more importantly, why the weird reducing agent? Well, because we need to reduce only the iminium ion. We don't want to reduce this aldehyde, all right? Aldehydes can be reduced. They're susceptible to reduction. In fact, they're quite easy to reduce. So we really need something super mild that can reduce them, and sodium cyanoborohydride does that for us, all right? If you reduce the aldehyde before the reaction begins, then boom, game over. You're not going to get anything, all right? So sodium cyanoborohydride is what your textbook advertises, and it actually works quite well. The problem is it's toxic. All right, it does have a cyano group that is can be released from the boron and, cause some issues with ionic cyanide. So it's been replaced mostly in laboratories by something called sodium triacetoxy borohydride. All right, so that's going to be this guy. All right, so what does that thing look like? It has these acetyl groups. Sorry, acetate groups, OACs, which are all electron withdrawing, thus attenuating the delta minus on our hydride. All right, so it does the same thing. It just doesn't have the toxic cyanide liability associated with it. All right, so again, let's just practice looking at an reductive amination. Why don't we take a ketone this time for fun? Take acetophenone. And we're going to take a secondary amine. Let's take diethylamine. And have acid. And sodium triacetoxyborohydride. So reductive amination is usually easy to spot because of the reducing agent that's in there. All right. So sodium triacetoxyborohydride or sodium cyanoborohydride, that should tip your hand that you're looking at a reductive amination. Okay. So again, what's going to leave? We're going to lose oxygen here. Okay. Oxygen is going to be gone, and we're going to add nitrogen in its place, but we're going to do that reduction. Okay. So what I want you to be able to see here is that we make this guy stays, and we make a bond to nitrogen where the oxygen was. But it's only a single bond because of that reduction, okay, step by the sodium, or in this case, triacetoxyborohydride. So the nitrogen is going to keep its alkyl groups, but lose that hydrogen, okay? Nitrogen is always going to be losing one hydrogen in this process because it gives it to oxygen during that proton transfer that we saw in the mechanism, all right? So it can leave as water. So nitrogen is going to attach to the carbon where oxygen was with a single bond. It retains all its alkyl groups and gives up one single hydrogen in the process, all right? So here we went from a what? Secondary amine to a tertiary amine. Is it clear why it's tertiary? Nitrogen has a carbon there, and a carbon there. Okay? So very effective way to make secondary and tertiary amines from from amine-containing compounds. All right? Okay. I will go ahead and stop this video here, and hope to see you around for the next one.